Okay, students, now we'll talk about section 11.6, which is angular momentum. As always, we will start by using the linear quantity. The linear quantity of momentum is P. The linear momentum is equal to the mass multiplied by V. Now, easily, if we just use the radius r to convert the motion from linearly to rotational motion. Before we convert our formulas to angular formulas, the angular momentum sample is L, okay, not P. If we have M in linear motion, the effective mass in angular motion is moment of inertia, as we say before. The velocity in angular motion is omega. So the momentum in linear motion is equal to mv, will be equal in angular motion I in the place of m and omega in the place of v. How is that happened? If we just multiply the both sides by r, rp is equal to rmv, rmv, v is equal omega r. We know that. Now just take this r to here, this r, we have two r's, then it will be r squared. Omega is omega, m is m. M multiplied by omega by r squared is moment of inertia, and r multiplied by p is angular momentum L. Okay, this is how we can find the formula of angular momentum. It is the same. It is mass multiplied by velocity. It is effective mass and rotational motion multiplied by the angular velocity. Okay, now how can we find the force in linear motion? Just the change in momentum over the change of time, which is equal to, we know that the momentum is mv, as we know here. So the change in momentum will be m delta v. If we apply the change in momentum, the mass is constant, then the change will be just on the velocity. Okay, the change in momentum is m delta v. Delta t in the denominator, it will be delta v over delta t, as we know this from before. Delta v over delta t is the acceleration. The mass is the mass. We know that the change in momentum over the change in the time is the force, which is ma. Okay, the same. The change in angular momentum will be the change in omega, because the mass or the angular mass or the rotational mass or the moment of inertia, we need to call it moment of inertia, multiplied by delta omega over delta t, which is alpha, which is angular acceleration, and delta angular momentum over delta t is tau, which is Newton's second law in rotational motion. This is all for this section. We need to solve examples. Okay, if we have a moving ball, two balls, one they are moving around a person, they are away from him in distance r. Okay, look at this ball. This ball is rotating, and its motion, this is v for this m1, and this is r between the man and the ball. This is the direction of r, and this is the direction of v. The angle between them is 90 degrees. Now we have another ball comes in this direction. This is r direction, and this is the velocity. The angle between them is theta. It is not perpendicular. So this ball don't move in circular motion. It is just pass. near that person. If r is equal to 2 meters, the first mass for the first ball is half kilograms and its velocity is 2 meters per second in this direction. And the mass of the second ball is a quarter kilogram and its velocity is 3 meters per second in this direction. Theta 1 is 90, theta 2 is 40. Okay? What is the effect of theta? We will see that now. We need to find L1, L2, angular momentum for the first ball, angular momentum for the second ball, okay? L1 is equal to I1 multiplied by omega 1. Or, as we see from here, we know that L is equal to I multiplied by omega. Also, it is equal to R multiplied by B. So this is the second form. R multiplied by B is equal to L. But we need the perpendicular distance between the person and the mass, the rotating mass. So we need to put sine theta. It is not here, but I will put here in the example. So L is equal to RP sine theta. Theta is between R and P. P in the same direction of V. Okay? This V have the same direction of P. Okay, let us solve for L1 for the first ball. R is 2 meters. The mass P is equal to mv. The mass is half kilograms for the first one. Its velocity is 2 as given. Theta is 90. Sine theta is 1. So the angular momentum for the first ball is 2 kilograms meter square per second. We will see how we find this unit. Okay, the angular momentum for the second ball, we have different theta. R2, P2, sine theta 2. R2 is the same R, which is 2 meters. P2, M2, V2. The mass is 1 over 4. V is 3. 1 over 4 multiplied by 3 sine 40. This will be equal to 0.96 kilogram meter per second. How can we find the unit of the angular momentum? The angular momentum, as we see, is equal to R multiplied by P. R is a length, its units meter. Momentum is kilogram meter per second. So we have meter square, kilogram, second. Okay. Now we have another example. This is comprehensive example. It is long. It is easy when we divide it to pieces. We have a car going through a traffic circle, okay? We have 3 positions at A and B and C. We have RA is equal to RB, but they are not equal to RC. Okay. The car entered the circle at t equal to 0. But at the point A, the time was 3 seconds. After 3 seconds, the car passes at E. At t equal 5, the car was at B. At t equal 8, the car was at C. Okay? The velocity. Its velocity at A is 3 meters per second. This in seconds, okay? Its velocity at B is 5. Its velocity at C is 6. Okay? What is the radius? The radius at R is 14 meters. Also at B, A and B are 14 meters. At C is 20 meters. Now I need to find omega at each point, and I need to find the moment of inertia at each point. and the acceleration, and the angular acceleration, and the torque, and the force, linear. This one is linear. The acceleration is linear, but the angular acceleration is angular. The torque is angular quantity. P, which is linear quantity, but L is angular quantity. And the mass of the car is 1,000 kilogram. Okay, let us at first find omegas. Omega, as known, is equal to V over R at each point. So at A, the velocity is 3. The velocity, yes, is a 3. And the radius is 14 meters. Then the angular velocity will be equal to 0.21 radians per second. Okay? And so on. We can find it for the two other points. Moment of inertia. We need to assume that the car is a point mass. Okay? We don't need to take it as an extended mass. So the moment of inertia is equal approximately, okay, to m multiplied by r squared. M is 1,000, r is 14. Then the moment of inertia is 196,000 kilogram meter square. Kilogram, the unit of mass. R square, it has the units meter squared. The momentum, linear momentum, is equal to mass multiplied by the velocity at each point. And you can see the values of each momentum for the car at each point. Okay? Now, the angular momentum is R multiplied by P. And theta, in these cases, all of these cases, theta is 90 because the velocity is perpendicular on the radius. Theta is equal to 90. So sine theta is equal to 1. This is the angular momentum for the car at each point. 42,000, 70,000, 120,000. Okay? Now we need to find the acceleration. The acceleration is between the points. So we have acceleration at this period and we have acceleration at this period. Not at each point, but between them. So we have the velocity at A, at B, at C. At the time at A, at B, at C. The acceleration is the change in velocity over the change in time. This minus this over this minus this. So the acceleration between A and B is equal to 1 meter per square second. The acceleration between B and C is 0.33 meters per second squared. Okay? And the angular acceleration is the acceleration divided over r. This is the value at A. But look here. We have two radius at B and radius at C. The angular acceleration when the car at B is this value. But when the car go out in the outer shell and be at C, come to C, it has a different angular acceleration because the radius is different. Okay? We can find an average value between them when the car go through this track. Okay? The force is equal to m multiplied by the acceleration in two cases. The torque is equal to radius multiplied by the force multiplied by sine theta. Theta is pi over 2 or 90. It will be 1, the sine. So this is the torque at the point A, 14,000 at this point. And we have the torque at B and at C. Okay? We have two torques. Also, we can find the torque and the force by using this technique. We know that the force is equal to delta P over delta T. We have the momentum at B and at at A, the change in momentum over the change in time, it will be the force. It will be the same value. We have the same force. Also, the force between B and C. Also the torque. It is the change in angular momentum over the change in time. It will be this value and this value. We will see that we have just one value for the torque if we use the angular momentum over delta t, but here we have two values when we use radius multiplied by the force, because here we have two radiuses or radii, okay? But here we find the torque along all this track, not at this point and at this point, okay? When we have the change in angular momentum. And go through this example step by step. It will be easy to be solved when you have it step by step, okay? Thank you.